Dr. Kirsten Hall, and I am super pleased to tell you that Dr. Hall actually sent me a lot of her accomplishments, so I didn't have to try to research it on my own, which I love when speakers do that. Makes for a much better introduction. So she received her PhD from Johns Hopkins University last year, and she is currently a Schmidt Science Fellow. So this is a program where it's a short-term fellowship where people take their science and apply it to a different area. And so she is studying atmospheric physics in the context of climate change now at the Harvard and Smithsonian Center for Astrophysics. And then she's doing that for a year, and then starting in September, she'll become a Submillimetre Array Fellow, again, staying at Harvard. Prior to that, she served for 3 years as a fellow for the Space at Hopkins program, which is another interdisciplinary organization. And she prioritizes diversity, equity, and inclusion in academia and participates in academic community building. Some examples of her community involvement are participant in the early career astronomy and astrophysicist focus session for the Astro 2020 Decadal Survey, and she was a participant in the 2019 Lindau Meeting of Nobel Laureates, where she got to, wait, you're not muted. Okay, so that was actually a really cool opportunity for her. She was a panelist, and she shared the stage with, I believe, 3 or 4 Nobel laureates discussing physics, basically, and dark energy and dark matter is what I remember from that. So she's had a very illustrious career in such a short time, and I'm very excited to see what she does next and hear about her current research. So thank you, Kirsten. Go ahead.
Thank you so much, Allison. I'm super excited to be giving you all this colloquium. I do, of course, wish it were in person. It would be really fantastic to meet you all, and I hear the weather is much better there than it is here in Boston. But this, I think, hopefully will serve just as well. So I gave you kind of a vague title, I'm aware, from quasar environments to Earth's climate. And so in my title slide, I'm giving a sort of subtitle, a unique approach to measuring quasar feedback and an interdisciplinary postdoctoral experience. So this picture on my front slide is an object that I love dearly. It's a quasar, but more specifically, quasars are supermassive black holes at the centers of galaxies that are actively accreting or actively consuming material. And as a result, they are ejecting vast amounts of energy and radiation into the surrounding medium. Now, these are also known as active galactic nuclei, but quasars are sort of the brightest such category of AGN, of active galactic nuclei. And the talk I'm going to be giving is in the context of a concept known as negative feedback. This is the idea that this energy output in this, like happening in this video that I'm showing here, sends a shock wave traveling through the interstellar and possibly even the intergalactic medium of the host galaxy, and has the potential to wipe out or shut off or just really heat the environment such that stars can no longer form. And so that's the motivation, the little context, this nice little video from Goddard that I'm giving you. But before I go any further, I just want to present you with a little bit of an outline, because I think this talk is kind of a doozy since I'm covering some unrelated work at the end. So like I said, I'll tell you a little bit more about quasar feedback in the context of galaxy evolution. And then I will talk about the multi-phase nature of quasar-driven winds, and specifically look at how do we measure the most elusive component of quasar winds. And then I will present you with a really unique measurement of quasar winds that I worked on throughout my PhD. It probably made up about 3/4 of my thesis or so. And I'll tell you a little bit about what's next for me in this topic. And then I'll spend probably the last 10 minutes or so talking about being a Schmidt Science Fellow, this idea of an interdisciplinary pivot during a postdoc where I'm studying atmospheric and climate dynamics. So let's dive into quasar feedback in the context of galaxy evolution. So specifically, I'm talking about radio quiet quasars. This is a class of quasar. They make up about 90% of all quasars. So these really luminous AGN are mostly categorized as radio quiet. And this doesn't mean that they don't have any radio emission, but it means that the ratio of their optical emission to their radio emission is extremely high. So they're very, very bright. So what I'm showing here is an HST observation of quasars, and you can see that they just look like stars. They're just extremely bright, and it's really difficult to resolve information about the host galaxy. And so we end up with a lot of artists' renditions. Here's, this wind being launched from the galactic center, expelling material, heating material, etc. But the really amazing thing about quasars and the fact that they're so bright is we can see them out to very large distances. So this graphic on the top right here of my screen is from the Sloan Digital Sky Survey, and every single cyan point is a quasar. Which, as I said, so we see out to high redshift. I think the highest known, highest observed quasar is at a redshift of 9 or something like this. But we can really statistically measure them, observe them out to redshifts of about 4 or something. And so, like I said, these quasar hosts, we see them out to high redshift, and the number density of quasars actually peaks around a redshift of 2 to 3. This is going to be an important point. They actually tend to reside in star-forming galaxies, so galaxies that are typically more active as opposed to their counterparts that I'll tell you about in a moment. And they live in halo masses, so dark matter halos that have a mass of around 10 to the 12 solar masses. So these are the objects that I want you to keep in mind, as opposed to these radio AGNs. So these peak at the number density peaks at lower redshift. They have these huge relativistic jets that are very collimated. People study a type of feedback associated with them as well, which is why I'm making such a clear distinction here, but they tend to reside in elliptical type galaxies. There's not a lot of star formation going on, and they're massive. So they're around 10 to the 13 solar masses, so about an order of magnitude more massive in terms of their halo mass. And so just keeping in mind, I'm talking about these radio quiet quasar hosts in halo masses of around 10 to the 12 solar masses. That'll be important. But the reason I'm going on and on about where the number density of them peaks, et cetera, is that for something like 5 decades, astronomers have been studying quasars in connection with star formation in the universe, like studying feedback from AGN. And more specifically, when we look at cosmic star formation rate density, so this is solar masses per year per megaparsec as a function of time. So this is a look back time, going back in time to the right. We see that star formation in the universe really peaked around a redshift of 2. This is 10 billion years ago. And then declines towards the present day. And of course, we can't help but notice how this sort of like connection, okay, we have a peak in the number density of quasars, then we have a shutting off of star formation. Quasars, AGN, they expel material, they heat material, but really trying to get at the observational smoking gun of observing feedback in action is incredibly difficult. And it's has a lot to do with the fact that these are so optically bright. Like I said, it's really hard to, it's really difficult to observe the host galaxy and to resolve details of these outflowing winds. Furthermore, when we look at predictions for the luminosity function or the number density of galaxies as a function of their stellar mass, we found early on that the observation, which are the data points, for example, in the left plot, doesn't match like the pure prediction if you just take into account cosmic baryon fraction from lambda CDM, you find that there is a pretty extreme discrepancy both at low masses and high masses. So the number density of low mass galaxies, high mass galaxies are over predicted with just plain old cosmic baryon fraction. And so the idea is that different types of feedback on low mass scales and high mass scales can work to reconcile such a discrepancy. So if you were to take a cosmic simulation of galaxy evolution and input energy injection from, for example, supernovae at low masses and AGN at high masses, low masses as well, you begin to be able to resolve the tension, or really the discrepancy rather. And so there's this really classic figure that I like to include, and I had the realization when I was preparing this talk that it's 2021 and it's been 10 years since this wonderful review by Joe Silk. And I just thought that was interesting because here we are, we're still talking about this. There's so many papers, so much really interesting work, just really looking for looking for that like so-called smoking gun, or you know, the real evidence of these different types of feedbacks on different scales, etc. So that's the motivational spiel that I have for you. And now I'm going to launch into talking about the winds themselves. So quasar-driven winds are actually multi-phase in nature. So there's a hot, low-density, volume-filling plasma that is interspersed with higher density clumps of material. And if we look at a theoretical picture, so what I'm talking about, like this is a very idealized sort of schematic, but if you have an outflow from the black hole, it sends, like I said earlier, a shock wave, and you have this shell shock of ambient gas. And what I should say is that quasar winds have been observed. We have observed, of course, this is how we know about them for sure. We've observed outflows of ionized gas, of molecular gas at extremely high velocities. When I say extremely high, I mean greater than 1,000 kilometers per second for both cases. Which is a really strong indicator that that the feedback dynamics are occurring. That such a it's strong enough to release material from the potential well of the galaxy, and certainly to heat the environment. But there are a lot of questions around the actual coupling of this wind to the surrounding medium. Furthermore, we have this region, this hot gas bubble, this post-shock region that is too diffuse now to be observed with any emission line diagnostics. So this is that hot, low density, volume filling plasma component. And so not just me, I mean, lots of people have thought about this for some time, but I started thinking about this really carefully and with my advisors, et cetera. And we said, well, how do we measure the elusive volume filling component of quasar winds? And once we do that, or if we can do that, which phase carries the most energy, mass, and momentum? Like, how can we begin to couple this energy output to the interstellar medium of the galaxy? And so the answer to this question is through the thermal Siniaev-Zeldovich effect, or the TSE effect, as I will continue to refer to it. And this effect is the inverse Compton scattering of low energy CMB photons off of free electrons in a hot gas. So here I'm showing CMB is cosmic microwave background. Of course, this is the first light released after the Big Bang. And it has been propagating through the universe, cooling, and we now observe it in microwave emission. And you have this low energy CMB photon happily going along, and it hits a bubble of really hot gas with free electrons, and those photons get scattered or Bloom shifted to higher energies. And this has primarily been used, the TSE effect, to observe, detect, and determine physical properties of galaxy clusters. So what I'm showing here is this little schematic. You have a nice galaxy cluster with some ALMA data superimposed where we see this big hole. And this is very characteristic of a galaxy cluster. And I'll tell you why in a moment, but basically there's just, we have this virialized dark matter halo with really hot gas, and this is producing the thermal Sunyaev-Zel'dovich effect. And many telescope experiments such as the Atacama Cosmology Telescope, as well as, so that's ACT, as well as ACT-POL, the next generation, and the South Pole Telescope. These are sort of the highest resolution. When I say that, I mean about 1.4 arc-minute resolution CMB surveys of the sky. And they're able now to detect and measure the physical properties of galaxy clusters out to 1.5 and even beyond. So the TSE effect is a really powerful tool. And so let's get into the physics a little bit more. So these cosmic microwave background emits as a black body, essentially. So this is intensity versus frequency. And so you can see this dashed curve is the emission from the CMB. And when those photons hit the gas and they, like I said, they get shifted to higher energies, the way that this shows up in the spectrum is through this specific spectral distortion. So the shifting of the spectrum to higher energies. And what that means is you end up with a decrement or a lack of flux below 220 gigahertz and an increment, extra flux, above 220 gigahertz. Such that if you were to look at the difference of these two, you'd get the lower right-hand plot. And you can see here with the delta intensity being negative. Now, when we look out in the universe, we collect a bunch of photons at all different wavelengths, and they give us a lot of flux, right? They're really, this is the only way in the context of galaxy evolution, in the context of observing galaxies, that you're going to end up with a negative flux. There aren't other physical mechanisms that are taking emission away. So this is a really powerful signature, the TSE effect, the fact that you get this negative thermal Sunyaev-Zel'dovich effect here. And it's really powerful because it's redshift independent. This is just a shifting of the CMB. And so the amplitude of that delta I is directly proportional to the amplitude of the SE effect. And the amplitude of the SE effect is directly proportional to the total thermal energy of that intervening gas bubble. And I will get to that, and I can show you a little bit more detail a little later. So that's what we're keeping in mind. This is how we're going to use the SE effect to probe the total thermal energy of quasar bubbles, of quasar wind output. So let's move on to the measurement itself. Okay, so quasars, I already said, it's not that they don't have any radio emission, it's not that they don't have millimeter emission of, full spectrum, but they are extremely bright and optical, and they actually are relatively weak in the millimeter, such that especially with these CMB experiments, like what I was describing with ACT, the sensitivity and the resolution are not exactly high enough such that you can just detect individual quasars at millimeter emission. And so instead, we need to implement a statistical analysis. So this is done by cross-correlating or stacking the millimeter data on the locations of quasars. And so this mean stack is the exact same as a zero lag cross-correlation. And you can then, draw out the average millimeter emission from quasars. And so this is what we do, but we don't just want to look at the millimeter emission. We actually want to include sort of radio through the infrared so that we can have an anchor point for the emission in the quasar and its host galaxy. And so then we can model the broadband spectral energy distributions and include known sources of emission plus the SE distortion. So that's the method that you should have in mind as I go through and start showing you spectra. So the rest of the data, so as I mentioned, the Atacama Cosmology Telescope, this is spanning the TSE. So the decrement is going to be 95 and 150 gigahertz. The null would be at 220 and the increment at 277. We also added radio data from the Very Large Array. So this is survey data. The 1.4 gigahertz is the first survey, and 3 gigahertz, there's this nice pilot survey that's available. I think it's something like 50 square degrees on the sky at 3 gigahertz. So we could have sort of 2 data points in the radio regime. And then, of course, a telescope that I really love and wish we could have a sort of 2.0 is the Herschel Space Observatory. We use both the Spire and PAX instruments, so we get a full coverage of the dust spectrum, all the way from 100 microns to 500 microns. All right, and of course the Quasar catalog is coming from the Sloan Digital Sky Survey. This is spectroscopic, the largest spectroscopic catalog of quasars. And we did this because this could be really interesting with lots and lots of photometric quasars, of course, as well. We could add many, many, many more, but actually being able to divide into redshift bins is an advantage that I will touch on in just a moment. So in the total survey footprints, which I'm showing on the lower right, so you can see we have several different ACT fields. So ACT is not an all-sky CMB survey, but rather has several different footprints that are relevant here for coverage that also covered by SDSS quasars. And in total, covering all of these survey footprints, we have about 111,000 quasars overlapping in total all of these fields. And so I'm showing sort of the redshift distribution in different fields. This just has to do with, the differences have to do with just SDSS selection. But the black curve is the total normalized redshift distribution of quasars. And then we divided them into 6 redshift bins with equal numbers of quasars in each bin to perform the cross correlation as a function of redshift. And so these are exactly the cross-correlated stacked images that I was talking about, but I'm showing them specifically for the relevant region, the ACT data points spanning the TSE effect. So there's about 18,000 quasars going into each redshift bin. Those are the columns. And the emission that you see in the center is the emission from the quasar, or lack thereof. We saw something actually very surprising that we did not expect, which is that at low redshift, there's this sort of millimeter excess emission, and I'll say more about that in a moment. But more importantly, even when just looking at these stacked images before doing any modeling, we can actually see the SZ decrement showing up, this negative flux beginning to show up in the total 95 gigahertz stack, and potentially an SZ increment, but this is, of course, we can't pick out an increment with our eyes. And so now I'm going to show you these broadband spectral energy distributions. So these are the 6 redshift bins increasing across the top and the bottom. And just to orient you, these spectral energy distributions are increasing in frequency. So this is flux density as a function of frequency. So we have the VLA data points on the far left of each plot. In the middle are the ACT bands, and on the far right covering the dust spectrum. And as you might recall, I said we need to model all of the known emission mechanisms so that we can get out the TSE signal, because actually the TSE signal is quite faint, like it's very small in terms of total flux density. And so we need to do some really careful modeling. And I implemented just you can see a synchrotron spectrum in the radio. And in the far infrared and spanning the infrared, we actually have 2 modified black bodies, a cold component and a warm component for the quasars to fit the total infrared dust spectrum. And in the middle, we have our ACT bands. And of course, like I said, we observed this very strange millimeter excess. So no iteration of synchrotron plus dust spectrum is powerful enough to fit this excess that we observed at 95, 150 gigahertz in the lowest redshift bin, 95 here, and 95 all the way out to a redshift of 1.9. And in the basic model, we attribute this to CO emission. So this is the 2-to-1 and 1-to-0 lines that actually enter into the ACT bands at these redshifts. And so that's kind of all I'm going to say about that for now. I might say one more thing, but if you want to talk more about it, let me know. I'm happy to. It's very interesting. It's unexpected. It took a long time of really trying to tease out what that excess emission could be. So yeah. More importantly, for the context of this talk, you can see that we begin to observe the SE decrement. So the red curve here is the total model being fit to all 6 redshift bins simultaneously. And you can see it's got this really funny shape. Why does the red curve, drop off and not match the gray dashed lines of the other sources of emission? Well, because of the TSE effect. So you can begin to see in 95 gigahertz at these high redshift bins, this is just the little error bar peaking above here. This data point is negative with an error bar, giving it consistent with 0, as with these two consistent with 0 flux. So this is a really, before even modeling the emission, just a really telltale sign that we have a measurement of the SE in quasars. And so the last thing I'll say about this millimeter excess is that we need more data in the millimeter regime. I don't think this would be an observational astronomy talk if I didn't talk, of course, about the need for more data, but truly radio quiet quasars have not really been studied in a statistical sense in the millimeter and in the radio regime. And so trying to figure out all the possible sources of emission would really be helped by having additional data here between 3 gigahertz and 95 gigahertz. It's a pretty wide range. So I'll just say that and move on. So for the rest of the talk, I'm going to focus on just the high redshift bins where these what I'm calling CO emission lines are not detected, and therefore we don't have this this degeneracy or discrepancy between the competing roles of the CO and the SC signal. So now I'm showing a residual plot. So this is just the 3 highest redshift bins. The total spectral energy distributions are fit simultaneously for all of those different emission components. By the way, there are a lot of other interesting parameters that sort of come out of that fit, but of course I just don't have a lot of time to cover all that. So if you'd like to know, I'm happy to chat about it. Just a moment, I'm going to get a sip of water. Okay, thanks. So what I'm showing now is the residual of the ACT data points. So this is 95, 150, 220, and 277 in these 3 different redshift bins. Residual after subtracting away the best fitting models for all known sources of emission. So the 2 modified blackbody dust spectrums and the synchrotron emission. And what we're left with, as you can see, is this very clear, very nice measurement of the SE decrement. And the red curve is the best fit to that. And you can see that the total thermal energy, as pointed out here, is changing as a function of redshift. And the reason for that is because we actually parameterize this, getting all the way back to the point, we parameterize this in terms of this feedback mechanism. So I mentioned earlier that the amplitude of the SE effect is directly proportional to the total thermal energy. And the reason that is because the SE effect amplitude is really an integral of the electron pressure over the total volume of that bubble. So this is the integral of PDV work that is then proportional to the total thermal energy in that bubble. And furthermore, we can parameterize this total thermal energy in terms of the total luminosity output of the quasars. So in particular, the sort of quantity of interest is this F, or the coupling fraction. So this is saying the total thermal energy is some fraction of the total luminosity of the quasar over the quasar lifetime. And so we need to know some information about quasar lifetimes. Again, we have over 100,000 objects, quasars. We just take sort of an average lifetime from the literature, something around 100 million years. But because this F and this tau are degenerate parameters, we just determine F in terms of 10 to the 8 years. And what we find is the coupling fraction over the lifetime of 10 to the 8 years is around 5%. So 5% of the total luminosity output of the quasar couples to the surrounding medium to produce the total TSE effect that we measure in the SEDs of quasars. And this is a pretty phenomenal result because 5%, somewhere around a few percent, maybe 1 to 10% of total quasar luminosity is actually injected into cosmic simulations that include feedback in order to reconcile the theory curve with the observed luminosity function of galaxies. So it's literally like this parameter that is being tuned, right, to help the theory fit the observations. And that tuning parameter is somewhere around a few percent of the quasar luminosity. And so this is super exciting. And before I just, continue to like, yay, we did it, look at this. This is such clearly this, here we are. I will say that, of course, I mentioned earlier that intracluster gas in dark matter halos produces the TSE effect, right? So I told you about how the TSE effect is used to detect and determine interesting properties of galaxy clusters. And that's because of this virialized dark matter halo of the really hot gas in the intracluster environment. And so, we're using ACT data, and we really need to be asking the question, do we measure a greater TSE signal than is expected in the halo due to quasar feedback, right? So we have some expectation for the amount of TSE that would be in a virialized dark matter halo of a few times 10 to the 12 solar masses. And we would expect that to produce some amount of TSE signal. And fortunately, there's a well-known relationship between the amplitude of the TSE and the dark matter halo mass. So this is from lots of measurements of galaxy clusters. It's measured down to around a few times 10 to the 13 solar masses. But if we assume that there's no problem that this relation should just extrapolate to lower masses, which certainly it should, then we can extrapolate down to the host halo mass size of quasars and determine how much TSE signal we would expect to measure. This part of the talk also has to come with a small caveat, because the halo masses of quasars is not just a known quantity. All quasars live in 10 to the 12 solar mass galaxies, but rather they do live in a range of halo masses, and this is known from autocorrelation function analyses, halo occupation distribution analyses, etc. And it turns out that quasars do live in halo masses of around a few times 10 to the 12 solar masses. So if we just take a range of stellar mass halos, and we look at what is the total thermal energy, we get up to 1 times 10 to the 60 ergs. So this shaded region down here, this is for a 2 times 10 to the 12 solar mass halos. It's a 5 times 10 to the 12 solar mass halo. You can also do calculations where you integrate over halo mass functions, which I have done. And what we wind up with in the literature, including the result that I just shared with you, is sort of this distribution of data points trying to measure the TSE signal from quasar feedback. So I actually worked on this for the first time in 2016. For the sake of time, I didn't really go over that whole introduction, but we didn't include nearly as much data, and so that is what lended itself to doing another analysis. These two data points from Verdier 16 and Sergel et al. 2017, these are done with using Planck, and Planck has a much larger beam than ACT, so you're talking about 5 to 10 arc minutes in size. And so there are some known uncertainties and concerns around the dust spectrum and around the very large beam size of Planck. And so I provided us with this updated measurement in 2019, where we now have a better understanding of the dust emission and the radio emission contributing in the relevant frequency range. And so if, on average, quasars, these 100,000 quasars live in dark matter halos of around 2 × 10⁻12 solar masses, we're still talking about something around 90% of the TSE signal being due to this extra energy input from quasars. If instead it's an average of around 5 × 10⁻12, we're still talking about a 65% excess. So we're still talking about, somewhere in the range of a few percent of the quasar luminosity coupling to the surrounding medium and producing this extra total thermal energy. So this is super exciting. I think there's still some really interesting work to be done in terms of some of the things that I mentioned, such as the dark matter halo masses, any correlated signal. I think we understand the dust pretty well. And I actually worked on a different paper in 2018 looking specifically at the dust emission around quasars. So if you're interested in that at some point, let me know. I'd be happy to talk about it. But now I want to just say a few words about what's next in this particular subject matter. So I'm the PI of an Onward program which observed 2 quasars at redshift 2.3 and 3.3. Specifically to look for the TSE effect in individual objects. And the candidates that we chose were hyperluminous quasars with bolometric luminosities greater than 10 to the 47 ergs per second. And the reason for this is that there's some evidence that there is a, like I was just showing in terms of the way that I parameterized the feedback model, there's evidence that higher bolometric luminosity means greater TSE signal, of course. So going after these hyperluminous objects is sort of the ideal approach. And furthermore, I have now, I'm adding to the SED, the spectral energy distribution of these individual objects, plus a third object that I ended up applying for time on with the submillimetre array. So I have sort of a wealth of frequency range data coming in relation to these 2 objects. So these were just added in the last year. I think my second submillimetre array target just got observed a couple weeks ago. So that's very exciting. And so I'll be happy to, update you on how that's going in the future. Okay, so I think I've been talking for about 35 or 40 minutes. Hopefully I can spend the next 10 minutes or so just taking a little bit of time to talk to you about this Schmidt Science Fellows program, this interdisciplinary pivot that I've been doing. So here I am with my cohort of fellows, of interdisciplinary scientists who sort of took this really bold leap straight out of their PhD, straight out of our PhDs in order to study something new, to apply our skill set to something new. And specifically, the Schmidt Science Fellows, they are aiming to develop the next generation of science leaders to transcend disciplines, advance discovery, and solve the world's most pressing problems. So it's that last part that is extremely attractive, right? The fellowship itself is really predicated on the fact that the most difficult problems in the world that humans are facing really are going to require interdisciplinary approaches. We need a broad spectrum of thinkers with a broad spectrum of skill sets to tackle things like climate change and world hunger. And just the idea that when you bring in a new perspective with a very technical skill set, hopefully you're bound to learn something new. And I found this really attractive. I've actually also always been interested in well, I say always, since undergrad, I suppose, interested in atmospheric science and climate change. And I just really saw this as an opportunity to dive in and learn some new things, apply my skill set to something that is going to be a little bit more directly, have more of a direct impact on humans on this planet. Something that I really love. I love doing public outreach. I love the awe factor that astronomy brings to people, the inspiration that, you know, understanding the cosmic universe a little bit better brings to people. It gives us a really inspired perspective on being a human on this little planet, arguably the best planet in the universe. And so, yeah, I would love to bring that same inspiration to climate science, but not just, it's not just about science, right? It's about communication and policy and things like that. So I'll just give you a little bit of an idea of what I've been working on. So I'm working with the Atmospheric Measurements Group at the CFA, and they are such a diverse set of scientists. They do many things, some of which I'm highlighting here. So this is satellite-borne measurements of atmospheric composition. So these are our existing data sets. You can see here I'm showing like water vapor, this formaldehyde, NO2, ozone, these things that are all very important to understand in the context of atmospheric dynamics and climate science. They're also, I'm working with two of the project scientists for upcoming missions, TEMPO and MethaneSat. So TEMPO will be looking at across North America at very high temporal and spatial resolution to study tropospheric ozone and aerosols and their precursors. And MethaneSat, of course, will be looking at methane, which is an extremely potent greenhouse gas. And so this is just sort of a whirlwind of things. They work on retrieval of the data from the satellites to sort of generate images like this. But more specifically, I sort of dove in on working on a atmospheric dynamics and climate related problem. And this has to do with these phenomena, these events called atmospheric rivers. So this video is actually data of just this past January, an atmospheric river event that was occurring on the west coast of the US. So atmospheric rivers are the primary transport of water vapor from the tropics outward. And they are these collimated 2,000 kilometer long by 1,000 kilometer wide transport rivers, literal rivers of water vapor through the atmosphere. The flow rate is something like or greater than the flow rate of water at the mouth of the Mississippi River. And when they make landfall, they result often in precipitation. And in fact, I think that atmospheric rivers are responsible for up to 50% of precipitation on the US West Coast. So this includes snowfall, snowpack in the mountains, as well as rain. And so they can be extremely helpful, but there are different categories of these events, kind of like categories of storms. And when they are extremely intense, the result actually can be flooding and mudslides and other catastrophic occurrences on the US West Coast. And so understanding them, being able to measure the geographic trends, the recurring climate cycles of atmospheric rivers, the precipitation processes, as well as modeling and sort of flood preparation and warnings And really, actually, this is a big one, being able to detect them. So detecting them ahead of time is something that's difficult to do, but to really be able to see these intense events coming could be extremely helpful. And when you look at atmospheric rivers in the context of climate change, there's models to suggest that actually they are worsening in a way. So this particular study shows that there could be an increase in atmospheric river frequency of up to 50%, and that the strength of the atmospheric river would increase by up to 25%. So as you can imagine, this is really a really interesting atmospheric dynamic process that could have really rewarding consequences if we continue to get a better handle on them. And the second thing that I am thinking about, so I've been doing this for about 6 months now, so I think I'll just throw that in there as a little caveat, but just studying tropospheric ozone, which actually is so ozone, of course, in the stratosphere is very important. We like it. It protects the Earth from the sun's UV radiation, but in the troposphere can act as a greenhouse gas and a pollutant. And it's not directly emitted, but rather is created when sunlight interacts with other pollutants. But it also you can get stratosphere, troposphere ozone exchange. So this is, for example, during extratropical cyclones and other weather events, you can get these deep stratospheric intrusions that come deeply into the lower portion, the troposphere, and creating excess ozone in this region. And well, what do these two things, atmospheric rivers and tropospheric ozone, have to do with one another? Is that my new colleague, Helen, she published a paper in 2019 where she was looking at the retrieval of water vapor from the ozone monitoring instrument, saying this paper basically was just saying, we wrote this algorithm to make sure that we could retrieve water vapor accurately from the satellite data. And in that, she did a case study where she looked at an atmospheric river event on November 6th of 2006. So on the top row, I'm showing the average water vapor and ozone at about the tropopause. So this is the region between the stratosphere and the troposphere. And here I'm showing the water vapor and ozone on the day of the atmospheric river event. And here I'm showing the difference between the two. And it turns out that there seemed to be this ozone anomaly potentially associated with the atmospheric river event. And so this was very interesting, and it's really what I've been studying the most over the past 6 months. So I'm showing an atmospheric river event on December 11th of 2010. The red contours are the atmospheric river, and the green is the green and purple are the ozone anomalies. So after having subtracted away sort of the average December values. I'm aware that I'm running out of time, so I think I'm going to skip over this right plot and just say that I took a moment to kind of think about why this has been accessible to me, because I thought that might help provide some context. And in particular, there's just like a knowledge base that helps a lot. So programming in Python, IDL, MATLAB, those are the experiences that I have personally. I have knowledge of spectroscopy, molecular structure and dynamics, radiative transfer, statistics and modeling, map making and manipulating of large data sets. Other qualities about me personally, I'm extremely curious. I have like an eagerness to learn. Of course, I developed in my PhD amazing critical thinking skills, like just the ability to like read scientific papers, I think is maybe like underestimated a little bit. And so this is just to say that I think transcending disciplines, like thinking about interdisciplinary problems, is very approachable for physicists. And so with that, I will leave you with my summary. Remind you that I measured quasar feedback and found that the total thermal energy coupled to the quasar luminosity at a level of around 3 to 5%, and how this is really important and interesting in the context of galaxy evolution. And my PhD really equipped me to sort of do an interdisciplinary postdoc. I'm really excited because I'm actually starting the SMA fellowship in the fall, but it's here at the CFA still. So I've made connections and collaborations in this separate group, and so I think there's a lot of potential there for some amount of work to continue. So thank you so much for listening.
Hey, thank you very much for your very nice talk. We have time for some questions. Yes, Ben, go ahead.
How do we do?
Oh, sorry. Did somebody say something?
I said, how do we do questions? Just talk?
Oh, I raised my hand using the reactions.
Oh, I didn't see raised hand on my thing. Go ahead. I'll be next.
Yeah, thanks. Let me just. Thanks for the great talk, Kirsten. I was just had a quick question about the percentage of energy that was coupled to, or sorry, the percentage of energy that the quasars were putting into their surrounding systems. Because you said that they were both degenerate parameters and you coupled it with the lifetime of a quasar. And I was wondering how you made how you made the qualification that it was 5% in the end compared to the lifetime of the quasar.
Oh, sure. Yeah. So so in terms of the lifetime of the quasar, basically we're just looking at some fiducial lifetime of about 100 million years, which is just some kind of like average taken from the literature, basically. You know, it could be a little more, a little less, but so we parameterize this in terms of the 10 to the 8 years. So you can kind of easily scale that up or down in terms of the quasar lifetime. The 3 to 5% is sort of more coming from the uncertainty in dark matter halo mass, right? So I was saying that at the high mass end, it's about 65% attributable to this excess energy is attributable to quasars. So that's kind of where the lower percentage end came from.
So was it just coincidence that it fit the models from the simulations, or was it that done on purpose?
Okay, so it's certainly not coincidence and not on purpose. This is what the model says. This is what the data say. So we said we're fitting for the dust spectrum, we're fitting for the radio emission, and we're fitting for the spectral distortion from the TSE effect. And then we parameterize that in terms of the total bolometric luminosity, and this is what came out.
Oh, okay, I get it. Thanks a lot.
Yeah, of course. I see some other hands. Should I call on people? I see hands, so I see that.
Yes. So, so Greg, go ahead. You were next, I think, and then it's Mohammed.
Thank you very much. That was a really fascinating talk. I've got questions about both aspects. I'm going to ask about the astronomy part first, and maybe I can ask you offline about the climate stuff, because I teach some climate stuff in my intro astronomy class, so I'm very interested in that aspect as well. You binned on Redshift when you did your stacked SZ signal, but it's drawn from the Sloan spectroscopic sample. So you have spectroscopic properties of the quasars as well, like line widths and stuff like that. So have you thought or tried on trying to see whether or not the optical spectroscopic properties in some way correlated or with the thermal SZ properties by stacking in bins of spectral properties?
I love that question. I've thought a lot about it. I would love to do it. So basically, though, I would then be taking, well, this was my idea, right? Was to look at in each redshift bin, then further divide by, say, bolometric luminosity or some other physical parameter, like you say. But then I'm like cutting my total number down in half. And so what I was really going for in this study, as compared to previous studies, is shrinking my error bars as much as possible, right? Because I'm having to do this cross correlation, this stacking analysis. But certainly I have thoughts and plans to maybe look at broader redshift bins and divide further by those properties like you suggest. I think, yeah, definitely would be very interesting.
Thank you.
Yeah.
Okay, Mohammed.
Yeah, thank you. This was very interesting, diverse, and peculiar talk indeed. So I had a question about, like, in the beginning you said that the ratio of the optical emission to the radio emission is very high, and that's why the quasars are like very bright, right? So like, can't they be like emitting more radio waves and still be very bright? Like, yeah.
Yeah, sorry. So just to clarify, what I was saying is that they're extremely bright at optical wavelengths. So when we sort of try to look at star formation properties and things like this, like resolving the host galaxy, that's very difficult.
So it has nothing to do with like the amount of radio waves they're emitting.
It has a little bit to do with it,
Okay.
in that the ratio of optical to radio is high. So there's a lot more optical than radio, as opposed to radio loud counterparts, which have a high amount of radio emission. These are these quasars that you see, these radio AGN with really amazing relativistic jets shooting out. But we were excluding those intentionally.
Okay, thanks.
Yeah.
Okay, any other questions? So I actually had a question about those atmospheric rivers.
Sure.
So you focus on the West Coast, but is it something more general, or is it specific to that region because of the rotation of the Earth and
Yes.
the ocean?
Oh, sorry.
Yeah, no,
What?
go ahead.
Okay. Yeah, it's not exclusive to the North Pacific. You also get atmospheric rivers hitting Europe and India and other places. I just was, for the purpose of this talk, focusing on the U.S. West Coast.
Okay.
This is Kelly. Can you hear me? Can I jump in?
Yeah. Hi, Kelly. Sure.
Hey, that was brilliant, by the way. I don't see a way to raise my hand, so I'm just jumping in. But this has been great, and I'm thinking of The Godfather and Al Pacino saying he was trying to leave and they pulled him back. So I hope that'll be the case with you. But your work with us has been absolutely wonderful. Thank you so much.
Oh, thank you, Kelly. So Kelly Chance is the PI of Tempo. He's my supervisor here at the CFA, and asked if he could join this talk because he's never heard me talk about my astrophysics work. So yeah, thank you so much, Kelly.
Oh, absolutely.